Okay, so now getting into the main content of what this course is about. We are going to start off with a sort of recap in some sense of memory mapped I/O and go a little bit deeper into the AXI bus than was covered in the digital systems course. So, it is primarily going to revolve around the MMIO model, right, the memory mapped input output model. We will be talking quite a bit about the handshaking protocols used in the AXI-lite bus interface and talk a little bit about how registers can be implemented. So, I will actually be showing you code, Verilog code corresponding to a register bank and how we can basically have the AXI bus in such a way, set up the AXI bus in such a way that we can read and write the registers that are present in that bank. Now, a lot of that will involve a sort of Verilog simulation demonstration, right, walking through how the Verilog code works and then actually looking at how we can simulate it. And part of that is I will be introducing a new tool over here for simulation which is called Cocotb. Cocotb is a Python interface which basically allows us to write a test bench in Python and interface it with modules that have been written in Verilog. So, what happens over there is that we will be using, unlike the iVerilog simulator that we were discussing earlier, there is another simulator called Verilator. By the way, iVerilog also could be used, but Verilator is a bit more powerful for larger designs, as we will see, right. So, what we will be doing is writing Verilog code and a Python test bench, combining the two using Cocotb, and we will see how it can basically be used in order to run once again self-checking test benches and also at the same time to view the waveforms that result from the simulations that we are performing, right. So, Cocotb brings this notion of time and a clock into the Python libraries that we are going to use and thereby enables it to talk to a custom module that we are writing in Verilog and basically drive it, make it sort of move forward in time and verify that the functionality is correct. So, I will be sort of showing a demo of how all of that works and using that in order to explain the different concepts involved in the implementation of the registers. And yes, we will finally be looking at a complete Verilog simulation of a small register bank. There will be 2 registers inside a Verilog module which I can write to and read from. So, what I am going to do now is to start off with a review of digital systems, right. So, a little bit about the background, digital systems and embedded C programming that we had talked about earlier, and this is a lightning fast review, right, what we call a 10,000 foot view. Obviously, the assumption is that you have already done the course and are comfortable with the concepts over here. So, at best this is sort of a refresher of some of the terminology that we use and that is all. In general, we have different kinds of logic gates that we use when we are constructing digital systems. Broadly, they are classified as combinational. The idea of combinational being that I give it a certain set of inputs and the output is completely dependent only on the present set of inputs. AND gates, inverters and so on are examples of combinational logic. So is the lookup table present inside every FPGA, right. So, the lookup tables that are used to build up the FPGA logic are also combinational gates which can be essentially programmed to act as any kind of arbitrary Boolean function, right, by directly sort of encoding the truth table into it. Sequential gates on the other hand have a very specific kind of behavior. They have one gating signal usually called the clock, and what we say is only when there is a edge or some transition on the clock will the output of this sequential gate change, right. Now, there are different kinds of sequential gates. The most common one is the edge triggered D type flip flop. So, for the most part that is the one that we are going to be focusing on over here, right. Edge triggered D type flip flops primarily because we have a very clear kind of functionality when there is an edge, a transition from 0 to 1 which is called a positive edge or from 1 to 0 which would be called a negative edge, depending on what kind the flip flop is sensitive to. When there is that transition, the output of the flip flop will basically take whatever was there on the input and copy it over to the output, right. So, that allows us to implement some kind of a controlled state transition. Only when the clock comes, the state of that flip flop the output of the flip-flop will change, which means that as long as the clock does not transition, I can retain that state. I have some kind of memory associated with my system, which I can then reuse and sort of use it in order to perform computations in a systematic manner. Now, using that, what we did was we said that sort of the arbitrary structure, the most general kind of structure that we can imagine for a digital circuit is there is some kind of notion of state which is encoded in the flip-flops present in the system, and there is some notion of compute which is mostly combinational logic, right. This can sometimes, this picture is sort of an oversimplification because I might find that I am actually implementing something like, let us say, a sequential multiplier, where clearly the compute is not just combinational, but there I am sort of making the difference and saying that the sequential multiplier is this entire system, it is not just the compute alone, right. And what I mean by that is, since a sequential multiplier takes n clock cycles to multiply two numbers together, it means that some part of the state is being retained as part of the multiplier, right. And the present state of the system is including whatever are the intermediate states of those flip-flops as we are accumulating the final result. And therefore, this computation only needs to look at one specific partial product step that is being added in each cycle in order to get the final result. Now, with this picture in mind, we further sort of divide it up and say that we can think of it in terms of a data path, which is basically a set of logic gates with enable signals or control signals associated with it. Most of the time what we need to do is we want to have a set of control signals or select signals going to multiplexers, right. And what those select signals are doing is, for example, deciding that you have a choice of many different inputs that could go into an adder or a multiplier, and the select signal decides which of those actually goes in there. Similarly, I could have an ALU, an arithmetic and logic unit, and the select signal might be used in order to decide whether it is doing an addition or a subtraction or a multiplication or some other kind of operation, right. So, these select signals are essentially one simple way by which I can control the output of whatever kind of computation I am doing, but it completely depends on the present state of the inputs and the present state of the control logic, and that state in turn is controlled by a separate piece of logic which is usually based on some kind of finite state machine or a variant of that, right. So, by having a finite state machine, what we can say is, by keeping track of my present state and some other inputs to the system, I can decide what logic, what outputs the FSM should have, which in other words means what kind of enable signals need to be passed to the data path, and also what the next state should be, right. And as we saw in the digital systems course, you can generalize this idea and make it such that I can actually have the next state transitions themselves encoded as part of an instruction, and thereby generalize the idea of a finite state machine.